My name is Daniel Hans, and this is a presentation video for my PBR ray tracer. Ray tracers work by shooting camera rays through the screen and into a scene. These camera rays will then intersect with objects, getting the object's color. This will be modified by the view angle and the angle between the light source and the intersect point by a shade function. This color can be further modified by shadows, which are calculated by shooting rays between the intersect point and the light source to see if there is an object in the way blocking the light, or by reflections, which are calculated by shooting an additional ray out from the intersect point to see if it collides with another object that could cause color bleeding. Inside my ray tracer, I've used PBR as the shade function. These are the part of the functions that handle both the diffuse and the specular color. The bidirectional reflective distribution function, which handles the specular color within PBR, is made up of three functions itself: the normal distribution function, a Fernald's equation, and the geometry function. I am using the Trowbridge-Ritzer GGX function as my normal distribution function. I am using the Fernald-Slick approximation as my Fernald equation, and using Smith's method with Slick GGX as my geometry function. I later hope to add depth of field to my ray tracer. This mimics how real life camera works by making objects that are closer/further away blurry. This is achieved by shooting supplementary camera rays through a focal point, which is determined by the focal length. These supplementary rays will make objects that are further away from the focal point blurrier. How blurry they are can be determined by the aperture size. The architecture of my ray tracer uses a single shade object, which all the scene objects and light objects are added to. Then for each pixel, a camera ray can be given, and the shade object will run the PBR shade function on the closest collision, having performed the depth test, and in return the pixel color. As my ray tracer draws a single pixel at a time, it can be multi-threaded by dividing the total number of pixels between the total number of threads. This lets multiple pixels be drawn at once, drastically speeding up render times. The plane object takes in its local vertex positions from external text documents. It is also capable of doing local depth testing with ray intersection. This allows a wide range of 3D objects to be added easily to my ray tracer just by adding more text documents. Here are some demo scenes that I generated using my ray tracer. All data collected for the analysis was gathered from this scene using these default parameters. This data shows the effects that increasing the number of threads has on the render time. As you can see, initially there is a dramatic decrease in the render time, however this levels off around 8 threads. This is because the CPU I'm using has 8 cores. However, the optimal number of threads is actually 16, which suggests that running 2 threads per core is actually more efficient. Here I demonstrate both soft and hard shadow implementation. The soft shadow looks more realistic as the edge of the shadow isn't solid and instead it fades as it moves away from the core shadow, while the core shadow still remains very black. This is different than the hard shadow where what is and what isn't shadow is very hardly defined, which leads to it looking unrealistic. As my ray tracer calculates shadows per pixel, I only calculate soft shadow on the initial camera rays. Reflection rays automatically use hard shadows as there is very little visual difference between the two methods, but a very big difference in the render times. These images show the effects the number of light samples have on my soft shadows. As you can see, the less light samples that are used, the more noisy the edge of the shadow becomes. However, increasing the number of samples also increases the render time. I found 400 samples to be a nice middle ground between noise and performance. The quality of the reflections are also affected by the number of samples taken. As you can see, the specular reflection taken from the metal sphere aren't really affected by the sample rate. However, the diffuse reflection coming off the floor is. As the less samples we take, the more noisy the reflection becomes. This is even clearer to see on the cube. However, as the number of reflection samples taken doesn't have a huge impact on the render time, we can normally get away with increasing this quite a lot to improve the visual quality. I've used PBR over a basic shade function, not only because the PBR looks better, but because it gives me significantly more control over the material properties of the object, including the metallicness and the roughness. This in turn lets me create better reflections, as diffuse reflections are not possible with a basic shade function. Having now presented the effects that sample rates have on the render time, I believe that the optimal number of samples are 400 light rays and 250 reflection rays, as this gives the best performance to visual quality output. Soft shadows are always worth it, as they make the scene much more believable, even though they also cost quite a bit more than hard shadows.